Welcome. In this video, we're going to take a look at the common ion effect and see how this affects acid-base equilibria calculations we might do. So first, we want to understand what the term common ion means. And this is when you have two substances in an aqueous mixture that both contain the same ion. So let's take a look at some examples. And we want to keep in mind as we're looking at this is when you have acids and ionic compounds, when you dissolve them in water, they tend to dissociate and form ions. So that's important to just remember here. So KClO, that is an ionic compound. So when I dissolve it in water, it's going to split apart into these ions, K+, and then the ClO- ion. Turns out that ion's called hypochlorite. You don't need to memorize that ion, but if you're not sure what the charge is, we know that K and ClO- add up to neutral, and we know from the periodic table that K must be +1, so we can figure out ClO must be -1. All right, and then HClO, this looks like an acid, so it's going to dissociate and make H+ and ClO- ions. So notice how these two substances have an ion in common. That's the hypochlorite ion. Sometimes you write it as OCl, or sometimes you write it as ClO or OCl-. It's a chlorine and an oxygen. Okay, let's take a look at another one. This is HC2H3O2 and NaC2H3O2. When they dissolve in water, they're going to split up and form these ions, the hydrogen ion, the sodium ion, and then they both contain the acetate ion, C2H3O2. So they have an ion in common. And let's look at this last example. These two substances look very similar. They both have a CO3, but if I break them apart into their ions, this is sodium and HCO3. This is the bicarbonate ion, if you're curious what the name is. And then this is sodium, and then this is CO3 2-. This is the carbonate ion. So these two actually do not have any ions in common. So we just want to be careful when we're looking for these common ions and make sure, oh, do they actually have an ion in common or not? All right, so now we've established what a common ion is. Let's do a quick refresher of what acids are. So what makes something an acid is that when you place it in water, it dissociates to form hydrogen ions. Here's a generic example of what an acid does. So here's my acid, stick it in water, it breaks apart, makes hydrogen ions, and then some anion. We're using the letter A for that. And you can write a K expression for this reaction. Since it's an equilibrium expression, we call this a Ka expression, since it's the K for an acid dissociation. So now let's look at an example. This is hypochlorous acid, HClO or HOCl. When you place it in water, it dissociates and makes hydrogen ions and OCl- ions. And this is the, oh, I didn't label this. This is the K value for this reaction. K is 3.5 times 10 to the -8. So we're looking at a couple scenarios. First scenario is what happens when we put HOCl in pure water. So we're dissolving HOCl in pure water to make a 0.1 molar HOCl solution. So we fill out our ice chart. I'm going to start with 0.1 molar HOCl, and I'm putting this in pure water. So the initial concentration of the ions is 0. And then I know that some of my reactant is going to get used up. I'm going to make some product. Notice how there's no coefficients here. So it's a 1:1:1 ratio. So that's nice. So this is 0.1 minus x. This is x, and this is x. And if we were to write out our K expression, so K is H+, whoops, let me give myself some more room. Our K expression for this reaction, it's products over reactants. So H+ times OCl- over HOCl. And I just realized in this equation, the states of matter are not labeled. So let's go back and label the states of matter in this one. They're all aqueous in this scenario. So everything gets included in the K expression. All right, so I've got my ice chart filled out. I've got my K expression. I know the value of K, so let's start plugging things in. So I know that K is 3.5 times 10 to the -8. And then my hydrogen and my OCl, those are both x. So it's x times x on the top. So I'm going to write that as x squared. And on the bottom, it's 0.1 minus x. And remember, anytime you have a K value that's small, meaning like much less than 1, look to see if you can make that K is small approximation. So as long as K is 3 orders of magnitude, so like 1,000 times smaller than the initial concentration, we can make this x's small approximation, which means we can say that 0.1 minus x is just 0.1. And then it makes the math a lot easier. So to solve for x, we go 3.5 times 10 to the negative 8, and then we multiply by 0.1, and we take the square root of the whole thing. So you can stop and plug that into your calculator. And then when I plug that into my calculator, I get 5.9 times 10 to the 10 to the negative fifth. And that represents my hydrogen concentration. So I can also, if I know the hydrogen concentration, I can find the pH. Because you might remember, if you look on your equation sheet, pH is the negative log of the hydrogen ion concentration. So since we got this number, let's find out the pH as well. So when I do that, it turns out the pH is 4.23. So this is when I'm dissolving HOCl in pure water. Okay, so we've just found the pH of a solution of HOCl in pure water. Now we're going to look at a scenario where we have a common ion. So we've got the same reaction. It's still HOCl dissociating, same K value, same K expression. But what's different is instead of dissolving HOCl in pure water, we're going to dissolve it in a solution that already contains some other ions. So we're dissolving enough HOCl to make, to make this a 0.1 molar solution. That's the same as our previous example, except now what's also present in the solution is some sodium hypochlorite. Whoops, sorry. So this is an ionic compound. So when you stick it in water, it's going to break apart into sodium ions and hypochlorite ions. So when we have our initial setup here, we're going to have 0.05 molar hypochlorite ions also present in the solution. And we don't mention any hydrogen anywhere, so we're going to assume this is still 0. So I'm going to go through and I'm going to fill in my change. So it's still, 1-to-1 ratio. So my change row is the same. This is 0.1 minus x. This is x. This is 0.05 plus x. And now I'm going to go plug these values into my K expression, this thing right here. So we know K is 3.5 times 10 to the negative 8. On the top, my hydrogen is x. My OCl is 0.05 plus x. And my bottom is 0.1 minus x. And we already established earlier that my K value is pretty small. So that means now both for this value and this value right here, I can make that x's small approximation. So what I can do is instead of saying 0.05 plus x, I can just call that 0.05. Because that change, x, is going to be insignificant compared to that original number. And the bottom just becomes 0.1. And feel free to skip straight to here too if you want to kind of skip this intermediate step. So now I'm going to rearrange and solve for x. So notice to solve for x, x is 3.5 times 10 to the negative 8. I'm going to multiply by 0.1 and then divide everything by 0.05. I don't even have to take the square root of anything here. So the math just kind of gets easier too when we have these common ion scenarios. So when I plug this in my calculator, I get that x is, is 7.0 times 10 to the negative 8. So that's my hydrogen ion concentration. And if we take the log of that, remember pH is the negative log of the hydrogen concentration. So if I know hydrogen, might as well calculate my pH. My pH ends up being 7.15. So notice how we saw a pretty big impact on my amount of hydrogen ions that form and my resulting pH. Because if we look back at the previous one, my pH was 4, and now my pH is 7. So we're seeing a pretty big impact here. So let's look at one more example. We're looking at HOCl again, but just slightly different scenario. So we're starting out with 0.1 molar HOCl, and this time we also have this common ion, but now it's 0.2 molar instead of 0.05. So we're going to see maybe an even bigger impact on my equilibrium here. So let's take a moment to do that. So I set up my ice chart. I'm going to plug it into my K expression. So K is 3.5 10 to the negative 8. The top is x. We're going to use my x's small approximation and say 0.2 plus x is just 0.2. And the bottom is 0.1. And I'm using my calculator and solve for x. And this time when I solve, I get x is equal to 1.8 times 10 to the negative 8. And that's my hydrogen ion concentration. So if I want to solve for pH, I'll see that my pH is 7.75. So what we should notice is that when we add a common ion, the amount of hydrogen ions decreases. So in that case where there's no common ion, our original one was just the acid, we made 5 times 10 negative fifth hydrogen. When we had a little bit of common ion, it was 7 times 10 negative 8. And we added more common ion, now it's about 2 times 10 negative 8. And notice that the pH is increasing each time. So when we add a common ion in this acid equilibria, it causes the amount of H plus to decrease. So notice when there's a common ion, we make less hydrogen ions. And then as a result, if we have less hydrogen ions, we'll observe that the pH ends up increasing. Like in our example, the pH, just the acid and water, was around 4. When we put in a little bit of common ion, it went to around 7, and here it went to around 7.7. So we see the pH increasing because we're making less and less hydrogen ions in these scenarios. That same thing though, when you have a common ion, the main idea is that when you're filling out the initial row, the idea of a common ion is you're already starting with some products present in your initial solution. So that's the big impact in terms of our ice chart setup. All right, let me know what follow-up questions you have.